Hi everyone, and welcome to this session of the PSMA training, which is an introduction to agent-based simulation using a Python package called MESA. Now, earlier in the course, we talked about agent-based simulation briefly when we talked about all of the different simulation types. But today we're going to be really exploring agent-based simulation, and you'll be seeing the differences between this and the discrete event simulation stuff that you were doing when you were using SymPy. So what is agent-based simulation? Well, agent-based simulation effectively, unlike SymPy and discrete event simulation, where you're focusing on a queuing model essentially, you're looking at the queues and how the queues are building up, where the bottlenecks are, and you're modeling everything as a series of processes, activities that people queue up for, and you're looking to reduce those queues. Agent-based simulation is very different. Agent-based simulation focuses on the individuals and the individual behaviors, the way they interact with each other, their motivations. And what we're really looking for is to see what the emergent behavior out of all of these individual level behaviors is. And very often in real world settings, actually, we see complex emergent behavior from lots of individual behaviors, individual interactions that are often much simpler. Because of that, it's actually commonly used in ecology, in ecological modelling, where it's used, for example, to model individual foraging behaviours. So, and in ecology, it's known as individual-based modelling more commonly. And in these situations, we may know, for example, lots about how an individual forager forages for food, the basic sort of behavioural rules that they would adopt in order to forage and look for food. But we might be really interested in the complex population level dynamics that emerge from those simple rules. It's also agent-based simulation is used extensively in modelling the spread of disease outbreaks in public health, and in today's session, it's actually going to be a disease model that we look at because it's one of the best ways to teach you how agent-based simulation works. But at the end of this course, I want you to be thinking about how the principles that I teach you today can be used in some of your own situations. How can agent-based simulation be used to represent some interesting systems within policing? And there's already some ideas that I'll discuss later. The other thing to say about agent-based simulation is it's actually different to conventional mathematics. For example, the formation of a snowflake can't actually be described using conventional maths, and so there's a whole field of field thinking that shows that things like agent-based simulation and something called cellular automata, which I'll show you in a moment, can actually be used to describe these things that we see in nature that actually can't be described using conventional mathematics. In other words, these are things that have very complex structures, complex emergent structures, but actually, agent-based simulation, cellular automata, demonstrates that these complex things can actually emerge from really simple cellular rules. So what are the key elements of an agent-based simulation? We've got agents. They're one of our key components in an agent-based simulation. And agents are things that move and interact within an environment. Now, very often our agents will be people, or in the case of ecological modelling, foraging animals. But it doesn't have to be. Agents can be other things and more abstract things as well. But in today's session, we'll be looking at agents as being people. Those agents will exhibit individual level behaviours and interactions, things that they do and ways in which they behave and interact with each other that then become important in the third element, which is the emergent behaviour, the outcome from our model. These individual level behaviours and interactions that, when viewed as a population level, actually lead to this more complex emergent dynamics. So I mentioned cellular automata briefly a moment ago, a cellular automaton is a type of agent-based model, and it's basically represented by a grid of cells, and each of those cells is either alive or dead. And one of the most famous examples of a cellular automaton is something called Conway's Game of Life. And in this cellular automaton, there are some really simple rules. The rules are that any cell that's alive in one generation and has either 0 or 1 neighbours, so the looking at the 8 neighbouring cells around that cell in the next generation will die from solitude or starvation. It doesn't have enough food or company. Any living cell with 2 or 3 neighbours in one generation will survive into the next generation. Any living cell with 4 or more neighbours will die from overpopulation. And any dead cell with 3 neighbours becomes alive. That becomes a birth moment. So these are 4 really simple rules. We can see that these are just very simple rules. Are you alive or dead? And counting your neighbours. And by applying those 4 simple rules, we then get Conway's Game of Life. And this is the cellular automaton we're looking at. Now, these are really simple rules, but what's really interesting about the Game of Life and cellular automata in general is that from those simple rules, very complex behaviour tends to emerge. And so I want you to go and have a look at this website. I've put the link up here on the slide, which allows you to play around with the Game of Life. And remember, the Game of Life is just those 4 rules that we just discussed here. So let's have a quick look at this website. So we can see here, we start off with a grid of cells. The grey ones are dead, the yellow ones are alive. If I click Start down here, it'll apply those simple rules to this cellular automaton. And you can see, quite interestingly, this initial little shape seems to be moving. And we haven't told it in any way to do that. We've just applied 4 very simple rules to get it to determine whether cells are alive or dead in the next generation. But there's a complex behavioural emergent behaviour that's coming out. And there are various shapes in Conway's Game of Life, various life forms, if you like, that have emerged. And this one is known as a glider. And if you click on the bottom left, you can see various different starting shapes. So something here called an exploder. So again, this is just a configuration of cells that are alive or dead. If I click Start, we're just applying those 4 simple rules. We can see that kind of an explosion pattern kind of happens. And these kind of life forms tend to emerge time and time again from this Game of Life. And remember, what's really interesting about this is that we have just applied these 4 simple rules. Nothing has told it to create this explosion pattern. It becomes an emergent dynamic of those simple rules. You can also, on this website, you can clear your screen and then choose different cells that are alive or dead just by clicking them, and different configurations, and then you can click Start and then see what happens to your particular configuration. So what I want you to do, just for the next 5-10 minutes, just have a little play around with this and see some of the different emergent dynamics that can come just from these really simple rules. Draw some of your own, explore some of the ones in the drop-down list, the different shapes, the starting shapes, etc. Have a play around with that, and then move on to video 2.